Hello, everyone. Welcome to our deep dive podcast, where today we'll be reviewing the paper VLA-Adapter, an effective paradigm for tiny scale vision language action model. Are you ready to explore the latest in vision language action models?
Absolutely. This paper is quite exciting, especially since it addresses the challenge of bridging vision-language representations to action in robotics, all while reducing the reliance on massive pre-trained models. Shall we start with the motivation behind this work?
Yes, let's do that. The authors point out that current VLA models, which connect perception and action, usually require large-scale vision language models pre-trained on robotic data. This approach, while effective, comes with high training costs and resource demands. Isn't that a significant barrier for many researchers and practitioners?
It definitely is. The need for huge datasets and powerful GPUs makes it hard for smaller labs or individuals to experiment with VLA models. That's why the VLA adapter is so interesting. It aims to achieve state-of-the-art performance with a much smaller backbone and without extensive pre-training on robotic data. Can you explain what the VLA adapter actually is?
Of course. The VLA adapter is a new paradigm that focuses on efficiently bridging vision-language VL representations to Action A. Instead of relying on large-scale VLMs, it introduces a lightweight policy module with something called bridge attention. This module injects the optimal condition into the action space, allowing the model to perform well even with a tiny backbone.
That's fascinating. So, the key innovation is in how the model connects perception to action, right? The authors systematically analyzed different conditions for bridging VL to A. What did they find in their analysis?
They explored which features from the VLM are most effective for action generation. They looked at both raw features and action query features, and also compared single-layer versus all-layer features. Their findings are quite insightful. For raw features, middle-layer latents are more effective than deep-layer ones as they retain richer multimodal details. For action query features, deep-layer latents perform better since they aggregate more information.
Interesting. And they also found that using all-layer features generally outperforms using just a single layer, right? That makes the design more universal and saves time on selecting the best layer.
Exactly. This led them to design the VLA adapter framework, which uses both all-layer raw and action query features as conditions for the policy network. The policy network itself is built with bridge attention, which integrates these features at each layer to guide action generation.
Let's talk a bit more about bridge attention. How does it work, and why is it effective?
Bridge attention is a module within the policy network that performs two cross-attentions and one self-attention at each layer. The first cross-attention uses raw features, the second uses action query features concatenated with proprioceptive state, and the self-attention operates on the action latent itself. There's also a learnable parameter that controls how much raw feature information is injected, ensuring stability and performance.
That's a clever design. By making the injection degree learnable, the model can adapt to different tasks and data. Now, how is the VLA adapter trained?
The training is end-to-end, with the policy network trained from scratch. The objective is to minimize the difference between the predicted and ground truth action trajectories, given the conditions from the VLM and the proprioceptive state. They use the AtomW optimizer and lower for efficient fine-tuning.
Great. Now let's move on to the experiments. The authors conducted extensive experiments on both simulated and real-world robotic benchmarks. What were the main findings?
The results are impressive. On the Libero Long benchmark, which is known for its complexity and low success rates, the VLA adapter achieved a 95% success rate with a 0.5B parameter backbone, outperforming much larger models like OpenVLA-Oft. Even when the backbone was frozen, the VLA adapter still performed strongly, achieving 86.4% success rate compared to 0% for OpenVLA-Oft.
That's a huge improvement. And what about efficiency? Did the VLA adapter also improve inference speed and resource usage?
Yes, it did. The VLA adapter achieved a throughput of 219.2 Hz and a latency of just 0.0365 seconds, which is significantly faster than previous methods. It also uses less VRAM, making it more accessible for researchers with limited hardware.
That's really important for democratizing robotics research. The authors also compared the VLA adapter to a wide range of baselines on the Libero and Calvin benchmarks. How did it perform there?
On the Libero benchmark, the VLA adapter achieved an average success rate of 97.3%, matching or surpassing state-of-the-art models that are 14 times larger. On the Calvin ABCD benchmark, which tests zero-shot generalization, it completed 76.5% of 5-task sequences and had an average length of 4.42, outperforming all baselines.
That shows strong generalization ability, even with a tiny backbone. What about real-world tasks? Did the VLA adapter perform well outside of simulation?
Yes, it did. The authors tested it on a 6DoF Cinria Alicia D robot with various pick-and-place, stacking, and long horizon tasks. The VLA adapter consistently outperformed baselines like ACT and OFT style variants, demonstrating better generalization and robustness in real-world scenarios.
That's impressive. The paper also includes ablation studies to understand the impact of different components. What did they find about the number of action query tokens and the types of conditions used?
They found that using too few action query tokens weakens multimodal aggregation, while too many introduce redundancy. The optimal number was 64 tokens. For condition types, combining all layer raw and action query features gave the best performance, validating their bridge paradigm.
And regarding the injection degree for the policy, what did the ablation show?
The ablation showed that the performance is best when the injection degree of raw features is learnable and the action query features are fully injected. This confirms the effectiveness of the bridge attention design.
Let's take a step back and discuss the broader implications. What does this work mean for the future of VLA models and robotics?
This work demonstrates that it's possible to achieve state-of-the-art performance in VLA models without relying on massive, pre-trained backbones and huge datasets. The VLA adapter lowers the barrier to entry, making advanced robotics research more accessible. It also opens up new directions for efficient model design and deployment.
That's a significant contribution. However, the authors also mention some limitations. Can you elaborate on those?
Sure. While the VLA adapter performs well, its generalization in real-world systems could be further improved, especially since it's not pre-trained on large embodied datasets. The quality of actions also depends on the conditions provided by the VLM, so future work could explore better representations and more complex training processes, like reinforcement learning.
That makes sense. There's always room for improvement, but this is a solid step forward. Before we wrap up, let's summarize the key takeaways from this paper.
Absolutely. The VLA adapter introduces a novel and efficient way to bridge vision-language representations to action, using a lightweight policy network with bridge attention. It achieves state-of-the-art performance on both simulated and real-world tasks, even with a tiny backbone and no robotic data pre-training. It's efficient, fast, and lowers the barrier to deploying VLA models.
Well said. This work provides a strong foundation for future research in vision-language action models and could inspire the development of even more advanced and accessible robotic systems.
That's all for today's episode. Thank you for joining us as we explored the VLA adapter paper. We hope you found this review insightful and inspiring for your own research or interests in robotics and AI.
Thank you, everyone. Don't forget to check out the project page at http://VLA-Adapter.github.io for more details and resources. Until next time, keep exploring and innovating.
Goodbye.